Fuel, air, and ignition. These are the ingredients for combustion, the spectacle that occurs within the cylinder walls of our engines. Changing the amount of any one of these ingredients can result in a more powerful engine, a cleaner engine, a more responsive engine, or an engine in pieces. The sorcerers that balance these three fundamental components to create more horsepower and torque seemingly from thin air are called tuners. These apostles of power dedicate years to mastering the art of balancing an engine on the thin line between maximum output and catastrophic failure, all while maintaining reliability and even better fuel efficiency. The tools of the trade used to be a screwdriver, some carburetor jets, and distributor weights. Now they are a laptop, interface cables, and expertise nothing short of a software engineer. This once praised and fruitful profession has in the last 10 years been the target of extreme government overreach and billion-dollar attempts to eliminate the practice altogether. The end of the tuning era is upon us, but how did we get here? Welcome to Explained. It all begins with a humble little chip, the erasable programmable read-only memory chip known as an EEPROM chip. Its purpose is to store a small amount of data, as little as 256 bytes, just enough for a boot program or operational data, and being non-volatile meant that when it was disconnected from a power source, the data would remain unchanged. By 1979, this tiny little chip would change the course of the automotive tuning landscape forever, thanks to Bosch's new Motronic engine management system. Motronic was a combination of an EEPROM that contained the program data for the fuel injection values and ignition timing, and a microprocessor using engine sensor data to calculate values needed for the next injection and ignition operation. In its first application, the 1979 BMW 7 Series, it was absolutely tamper-proof, maintenance-free aside from the standard spark plug change interval, and it was designed to last 500,000 kilometers. Little did BMW know that a young engineering student in California named Steve Dinan would not only find his way into the chip, but improve on the performance of their ultimate driving machines. To achieve this, his team used a clever process of deduction. They reprogrammed or burned half the EEPROM's values by an increment of 10 to see if it made any change on the ignition timing while using a timing light. If it did, then they split the data set of values again and again and again until they had a string of values that represented the ignition timing data. In raw binary, it was an unending sea of ones and zeros, but when it was converted to decimal values and plotted against an RPM and load axis, you had the ignition timing map, and therefore ECU tuning was born. The goal of tuning is to squeeze out every ounce of power that the OEM leaves on the table during the combustion cycle. One way is by modifying the ignition advance, or the amount of crankshaft degrees before top dead center that the air-fuel mixture is ignited. That initial spark ignites the fuel mixture as a wave over time, and the goal is to reach maximum cylinder pressure after top dead center at the optimal mechanical angle. The same theory is true with riding a bike. You don't push down the pedal at its most vertical position. You wait till the pedal is slightly past it before forcing it down and propelling you forward. The faster the engine RPMs, the more ignition advance will be needed to maintain that optimal angle, since there's less of a window for flame propagation. But too much advance will risk detonation, or the rapid overpressuring of the combustion chamber due to ignition happening outside of the flame front, which is highly destructive to engine components. Tuning really shines when not just software is changed, but hardware is also changed, like adding a less restrictive exhaust system, more aggressive camshafts with higher duration and lift, larger throttle bodies. These all do one thing: flow more air in and out of the engine. To maintain proper combustion within the engine, the air-to-fuel ratio needs to be taken into consideration. In gasoline engines, 14.7:1 AFR is perfect for idling and light throttle cruising conditions, since it is stoichiometric, meaning all the oxygen and fuel is burned completely within combustion. When at wide open throttle, you'll typically target 12.5 to 13 on a naturally aspirated engine and 10.8 to 11.5 on a forced induction engine, since a richer or lower AFR is needed at higher engine loads to curtail detonation. Different fuels have different stoichiometric ratios. E85, for example, has 9.7 to 1, and methanol is 6.47 to 1. To unify tuning between different fuels, tuners will read AFR in what we call lambda, which represents all fuel stoichiometric value as 1.0. No matter what fuel you're using, you will target, for example, 0.75 to 0.77 for a forced induction engine at wide open throttle, 0.85 for a naturally aspirated engine at wide open throttle, and 1.0 for idling and light throttle applications. All of these combined would drastically improve the performance of an engine. By the 2000s, the flash memory chips replaced EEPROMs, and no longer did the physical removal of chips have to happen to be rewritten or burned. These flash chips were faster to read, contained more data, and encrypted to protect the intellectual property inside. Not long after the introduction of flash memory ECUs, software engineers with a knack for performance tuning were cracking the encryption, creating tuning tools, and selling them to other enthusiasts looking to tune their rides. A plethora of companies spawned out of home garages to multi-million-dollar a year in revenue companies like HP Tuners, Cobb Tuning, Hondata, and SET. Now that tuning didn't require removal of chips and bulky equipment, just an OBD2 interface cable, some software, and some calibration expertise from your local performance shop. This became so prevalent that if you went to a car meet during this era, almost every WRX was using a Cobb access port, almost every Cobra Mustang was using SCT, almost every Camaro and Corvette was using a form of HP tuners. Companies racked in millions, enthusiasts were blessed with more power, higher rev limiters, and more boost, and it was a win-win for everyone.
Today, its new CEO said Volkswagen will fix 11 million diesel cars that were rigged with software that cheated on emissions tests.
There's one particular incident that has been the catalyst for the downfall of modern ECU tuning. In May 2014, a small West Virginia university team working with CAFE, or the Center for Alternative Fuels, Engines, and Emissions, found that Volkswagen 2-liter TDI engines produce 4 to 7 times the emissions when driven in normal road conditions than when tested on a chassis dynamometer. Volkswagen used what the EPA calls a defeat device, which was specially written engine management firmware that detected the position of the steering wheel, vehicle speed, the duration of the engine's operation that was indicative of the FTP 75 test procedure. In layman's terms, when the vehicle detected it was being sniffed, it would run much cleaner to pass emissions, but when driven in the real world, it was far more polluting. This would ultimately cost VW $33.3 billion in fines, penalties, financial settlements, and even jail time for certain individuals. This scandal single-handedly gave the EPA initiative to go after emissions defeat devices indiscriminately, no matter how small or large, manufacturer or aftermarket supplier. Any company that builds devices to defeat emissions were a target with a dollar sign. Another big hurdle was manufacturers were now spending hundreds of millions of dollars on developing unhackable ECU architecture. In the 1980s and 90s, the manufacturers used checksums, which was a number that represented the total of all the cell values stored in the programming. The ECM used this checksum as one way to determine if the contents of any cell had been changed, and if detected, would force the ECU into limp mode. As more powerful ECUs became prevalent, encryption became the standard practice, where the data is unreadable unless you have the key. The key can take a very long time to figure out. For example, in 2008, the Nissan GT-R boasted an unbreakable ECU, which in JDM trim limited the car to 180 kilometers per hour or 112 miles per hour unless it was on a racetrack. Cobb Tuning, within a couple of months, became the first to crack encryption on the Nissan GT-R, allowing for tuning of higher horsepower and limiter D restrictions. These ever-increasingly complex attempts to stop tuners from getting into the programming has raised the question, do you even own the car anymore? For example, on the C8 Corvette, which uses GM's robust Global B electrical architecture, if the ECU detects tampering of any kind, it will essentially become inoperable and leave you with no access to reset it. Even though you own the car, the manufacturer still owns the rights to the intellectual property in the ECU and won't give you access, well, unless you pay them undisclosed amounts of money to access the calibrations. This is creating an environment for tuners and aftermarket parts makers that, unless you have a team of software engineers dedicated to reverse engineering new ECUs, you probably won't be able to tune newer vehicles. And even if you succeed, the EPA can claim that you've built an emissions defeat device that violates the Clean Air Act and fine you out of existence. Even on the EPA website, they say, I quote, penalties act as an incentive for coming into compliance and staying in compliance with our environmental statutes and regulations, meaning you can operate, you just have to give us our coins. The way around it for tuning and part suppliers is to get a CARB EO number, which stands for California Air Resources Board Executive Order. This means your performance parts or calibrations meet California's emissions regulations, and since it's more stringent than the EPA's Clean Air Act, you are essentially 50-state legal and untouchable by the EPA. The only problem is this is a very expensive testing process most enthusiast shops and tuners can't afford, so they risk dancing with the devil and possibly getting a knock on the door from the feds. So what does the future look like for tuning? Well, it's simple. There will be a resurgence of older emissions-exempt vehicles to build and modify. For example, vehicles built before 1975 are smog-exempt since they don't require a catalytic converter, and diesels made before 1997 are also exempt under California rules, which are the strictest. Carburetors and distributors with the original tuning tool, the screwdriver, have a high likelihood of being the future of hobbyist tuning, as long as modern ECUs become uncrackable and the government entities crack down on the loose interpretation of emissions defeat devices. Do we all want to breathe clean air? Absolutely, without question. The less than 1% of vehicles on the road that are modified have no real effect on the quality of the air we breathe, and it would be disingenuous to think that the cammed Z06 chopping across the parking lot is diminishing your life expectancy when you probably vape. Days of buying a car, some commercially available software, changing a couple of values, and off to the drag strip on a Friday night may be behind us completely. But until that day officially comes, stay mindful and keep tuning.